Okay, so now we are going to talk about metallic sequence. Uh, Actually, in comparison with the Fibonacci sequence. Okay, so now last time we talked about metallic ratio that we denoted Mn, mu n. So now we are going to, it is given by half of n plus square root of n square plus 4. So this is for some fixed integer. If you fix some integer, some constant integer, like you fix it, integer which has to be usually greater than or equal to 1. It's greater or equal to 1. And then we can denote it by positive, mu n positive, as compared to another one, its conjugate, real conjugate, which is given by the difference, half of difference, n minus square root, n square plus 4. Okay, so now we proved that last time that mu n square, each one of them, is equal to actually mu n plus times n plus 1. This is what proved last time. Each one verifies this property, and also verifies each one verifies the property here. If we divide both sides by mu n, we are going to get n plus 1 over mu n. Okay, so now another interesting property that we have proved is if we multiply, for example, the first one, if you multiply by power k, of this one minus 1, you get mu n positive. For example, this is going to be equal to, as we have observed, so we can multiply both sides by k minus 1 on both sides, k minus 1 or k minus 2, k minus 2 on both sides, in order to get mu n plus power k. So we can multiply by k minus 2, power k minus 2 both sides, and get mu n power negative k power negative 1, and plus mu n k minus 2. So this we can denote it as vk, the first one. So it's equal to, okay, so let us denote it first by this one, mu n k minus 2, which becomes with this notation, which becomes n times z. Okay, this one, let us start. Vk minus 1 plus Vk minus 2. Okay, so we have seen that this is a recurrent relation, or recursive relation, which define this sequence as it can also be verified that it is a geometric sequence. So also, if we define another one like uk, which is equal to the second one, because it verifies this property, also it can be denoted mu n minus power k. So verifying this condition here, since it verifies this condition here from the characteristic equation here, so we might also have uk, which is equal to n times u not v, of course. Excuse me. So here we have u k minus 1 plus u k minus 2. Okay. So so this is also the same properties as this sequence, and for which vk is equal to mu n plus power k also, so that we may have this relation here. So with this, if you combine this relation with this one, combination of these two, so by the principle of superposition principle, so we can obtain another sequence, say wk, which is a combination of those two, and verifying the same properties, which is if I take wk minus 1 minus 2, so plus n wk minus 1. It means that you can get this relation when you obtain a sequence which must be a kind of sequence that we are going to call metallic sequence, which we have this form defining it for some initial values, initial condition, like for k equal to 0. Suppose we have like condition which are similar to Fibonacci initial condition. So like W1 equal to 1. Suppose these are initial conditions, and these are recursive relation which is defined to which is serving to define this sequence. So, and this sequence is what we are going to call metallic sequence with this notation. Okay, let me put it here. Okay, which will be metallic sequence. So the reason that we have called it metallic sequence, it is because it is an explicit function of the metallic ratio. This is the metallic ratio. Metallic ratio. So in this case, together with this recursive relation or recurrence relation, so we can define some few terms of this metallic sequence. So given the condition here, I can just remove this one. These ones as a function of this, we have the combination of these two, uk and vk, can be combined to define this one. So this can be proved. And then this one, the general term of this metallic sequence is wk with these initial conditions. So But if we use these two conditions, let us call it number one, subject to number two, these two conditions. So we can find some few terms of this sequence. So we are going to have, for example, for W naught, so we have 0, and W1 we have 1. Okay, let us write this down by index k equal to 0. We have W0, k equal to 1. We are going to have W1, and then, excuse me, so now with W equal, with k equal to 2, W2, then and so on, W3, W4, W5, W6, W7, and so on and so forth. Okay, so now let us use this condition to find some values, some terms. So for the initial condition, we don't have to worry, because we have, they are set to 0 as initial. They are set to 0. So this one is 0, the first one, and the second one is 1. Okay, so now others are going to be determined by using this recursive relation. So how does it work? It means that the one term, each term is expressed as a combination in terms of the two previous one, the closest to this one being WK minus 1. But before to add the previous one, we have to multiply by n. In that case, if you have the 1, if I have a k minus 1, I have to multiply by n. N multiplied by 1 is going to be n. And I add 0, no change. So next, if I have to find another term, I will have to take this term, I multiply by n, it becomes n squared. Then I add this term. So in that case, I will be getting this fourth term. Actually, this is the first, second, third, fourth. Fourth term, 1, 2, 3, 4. Okay, next. So if now we want the fifth, which is indexed 4, what you have to do, you take this one, we multiply by n, and then we add this one. And if you do so, this we have the highest power is the cubic plus, now this times n is 1 times n. I will add n, I will get 2n. So in this case, I will be getting the fifth term. So this is the third, and this is the second, and this is the initial conditions, and so on. Now the fifth, the sixth, the seventh, and the eighth. So we can find them in this manner by using these two relations. Let us keep them as we now know it. Okay, so here let us just define this space to use it, and then here I can just give other terms as I have calculated them. just before in preparing this video. So the sixth term will be, I can read here, is n power 4 plus 3 n power 2 plus 1. So the seventh term, 1, 2, 3, 4, 5, 6. Now seventh term is going to be n power 5 plus 4 n power 3 plus 3n. Now the next term is n power 6 plus 5 n power 4. So 6n power 2 plus 1 and so on. So we can calculate also n power 7. Actually this is gonna be equal w8 and so on, and we're gonna have n power 7 plus 6 n power 5 plus 10 n power 3 plus 4 n. And the next term will be maybe w8. This is the eighth term. Ninth term is w8. So it's gonna be equal 1, 2, 3, 4, 5, 6, 7, 8, 9. So w8, w9, it's gonna be equal to n power 8, 7 plus 7, n power 6 plus 15, n power 4 plus n power this 10 power times n power 2 plus 1, and so on and so forth until we get some term wk plus 1, wk plus 2, and so on. And we have few first term in this case. So as you can see, so these are a few terms for metallic sequence for fixed n, and you can choose it to be greater or equal to 1. Now let us take, now in case, for example, n equal to 1, for example, we are going to get this metallic sequence. It will become, so this one will remain as such. So this one will be 1, n equal to 1. So n1 plus 1 is going to be 2. Next time 1 cubic. So any power of 1 is going to be equal to 1. So 1 plus 2 is going to be 3. So here we are going to have 1 plus 3 is 4. 4 plus 1 is going to be 5. So here we are going to have n 1 plus 4 plus 3 is equal to 8. So the next term will be 1 plus 5 is 6. 6 plus 6 is 12. 12 plus 1 is going to be 13. So let us continue a little bit. So we have 1 plus 5 plus 6 is equal to, this is what I have just calculated. So now 1 plus 6, 7, 7 plus 10, 17, 17 plus 4, it is 21. This is 21. And so on. But as you can see, this sequence, the sequence you have here is exactly the Fibonacci sequence, in which case we consider the original initial values being 0 and 1. Okay. Now, suppose we take n equal to 2. What we are going to get is this sequence. So initial values are supposed not to change. So I have 0 and 1. The next one we substitute 2 because it's 2. So n is equal to 2. So n equal to 2 power 2 is 4. 4 plus 1 is 5. So now 2 power 3, 8. 8 times plus 4 is gonna be equal to 12. Now here we have 2 power 4, 16. So 4 times 2, 12. 12 plus 16 is going to be 12. This is 3 times 4, 12. 12 plus 16, it is 28. Plus 1 is 29. Okay, and so on. Okay, because calculation of power of 2, it becomes more a little bit confusing. It is not as direct as we had for n equal to 1. So this continues, and so on and so forth. So that so if we consider others for higher indexing of K, so for higher indexing, it will become this sequence. Actually, it is a very known sequence. We know it as this sequence. Excuse me here. So this sequence is commonly known as a sequence of Pairs number, or just Pairs sequence. Okay, so with these two examples, so we have a reason to call this sequence WK metallic sequence. Why? Because for higher indexing of K, so we can take the ratio of two consecutive terms, and when we take the ratio, that ratio converges to the corresponding metallic ratio. That is the reason why we call it metallic sequence. So we can have n equal to 3 and so on. And in the case of n equal to 1, the corresponding metallic sequence, I mean metallic ratio, mu1, it is called golden ratio. Golden ratio. And for mu equal to mu2, let us put it here with n equal to 2. So this is for n equal to 1. For n equal to 2, we have this one is the silver ratio. So of course, I don't know if we can call for n equal to 3 maybe copper ratio. I don't know. So, but these two are very well known, and they serve, of course, to define the sequence. Now, they are also going to be used to, the metallic ratio is going to be used to define the general term. We can give explicit form of the metallic sequence without using those two recursive relation. And this, we are going to do it by next time. So thank you for this video.